Howdy, we are the LaserWeed management team sponsored by the Department of AgriLife and the School of Innovation.
My name is Joshua Anderson, and I'm a computer engineer.
My name is Cameron Armand, and I'm an electrical engineer.
My name is Abigail Doherty, and I'm a computer engineering major.
And my name is Michael Go, and I'm an electrical engineering major.
So the project that we have been given is that weeds and weed management is a very expensive industry. And as people are trying to find new organic methods of weed management, they're very expensive and a lot of times very invasive. So our solution to this problem is to create a device that can be towed between crop rows, and as it's going between the crop rows, an camera will detect the weeds and then use a high-powered laser to shoot at the weeds and kill them.
So for the subsystem diagram, I'll be in charge of the power subsystem. Josh is in charge of the image processing with assistance from me. Cameron is in charge of the motor and laser control, and Abby, the laser research and design.
So here's a quick prototype of what our here's a quick mock-up of what our prototype would look like this semester as we were still working with it physically. You can see it's all mounted to a frame. This is our stable system. So our goal by this semester was to have a stable system not moving that could hit a weed that would be under this frame. You can see the camera and the Jetson are on top, and the NVIDIA and the laser gimbal is mounted towards the back of the frame.
For image processing, an Intel RealSense depth camera will be used to scan the environment, and a deep learning object detection algorithm called faster RCNN will be used for classification and drawing bounding boxes on the weeds. The camera outputs an RGB image and a depth image. The depth image will be used to ping the distance of the weed to the camera, and the RGB image will be grid mapped to determine the location on the plane. For this semester, we trained the algorithm on multiple datasets. On the left, you can see a picture of the object detection system drawing bounding boxes for a one-class. Next semester, we will need our sponsor to define the boundaries of the system because we will need to create a dataset that contains roughly 50 to 100 pictures. Challenges this semester for image processing is mostly that there aren't really any datasets online that are suited to our application. The best one we found, the Deep Weeds dataset, is a dataset created for classification of weeds rather than object detection. However, by the time we demo, this dataset will be correctly trained with our model. Challenges for the coming semester are that we will definitely need a more nuanced method of stem detection. Currently, we take the center point, 10% from the bottom of the bounding box, and send it to the motor system. This could cause problems for oddly shaped weeds. Also, current hardware is not sufficient to meet our target timing goals for the upcoming semester. A faster GPU would ideally be needed in order to implement a real-time response at speeds of 0.5 mile an hour and large numbers of weeds. For the image processing demo, we hope to take a subset of the Deep Weeds dataset, roughly 1,000 pictures that were annotated by hand. However, if for some reason this dataset is impossible to get to work correctly, we will use the Pascal VOC dataset to generate accuracy data and timing analysis. At the very least, we were able to get a small dataset that we created ourselves from the weeds we were given working, and we got an accuracy of over 90% for the real-world weeds. The picture to the right is an example of the Deep Weeds dataset being inferenced correctly by our object detection model.
For the laser subsystem, I have currently written code for the different tests that will be completed in the fall for the laser research. In order to complete this research, our sponsor will give us sample weeds. After validating the motor code, I will perform the tests for the research. I'll perform multiple trials of different types of tests. The tests will include firing at a single location on the stem and moving across the stem multiple times while the laser is on. Calibration for these tests will be done using a laser pointer before firing with the actual high-power laser. For the targeting, all code has been written and it works with the motor subsystem. As the weeds are detected, the coordinates are converted, the motors move to the proper weed location, and the laser fires for a sample duration. All of this code is mock-up and will need to be validated in the fall. The largest challenge for this subsystem this semester was performing the calculations necessary to convert the coordinates into motor movements. Here is an example of what the laser test code looks like. So currently it passes in an XYZ coordinate in inches, and then you can select the different type of laser test that you'd like to perform. In this case, I'm using a static test for 1 second. A lot of the values that we've had to use in the code is arbitrary. That'll need to be measured and validated in the fall. But as of right now, this code, it's currently going to a specific location, and then the laser is turning on, and then it'll be sleeping, and then the laser is turning back off.
Okay, so for my subsystem, I was mostly dealing with the servo controls, moving the gimbal, making sure we're going where we need to go, as well as taking those images and converting them into something that actually translates into real life movement, and then making sure that the motors are actually targeting and killing the weeds. My challenges were not being able to physically work with the device after spring break, which also made validation very difficult or near impossible for this semester. But we are working, we're trying with our code to get outputs that look like they would reasonably point to the right location. So you saw this code a little bit earlier, but here's a little diagram that kind of explains what's going on. So once a weed is targeted, it'll do a quick calculation on the side to make sure that we're getting to the right angle there. And then it converts that into steps in the motor. So the servos take a certain pulse width modulation, and it's a simple multiplication from that angle to get to the right amount of steps that we need. And then finally, I'm going to be doing a lot of validation next semester, but so I've been working on like a basic outline of how that's going to work. First step is to finish mounting all the hardware. So we're working with the stable system. I made this little camera mount that we're going to get printed as soon as we can. So we need to take some measurements at the top of my code, or our code. Currently, we have a few constants that we need to measure and get those. And then finally, we need to do some calibration. There might be some minor tweaks we need to make based on factors we haven't considered, like maybe the laser needs to be adjusted a certain way. So it's going to be a lot of just like dealing with the calibration and then making sure that we are in a reasonable amount of angular accuracy and not getting huge amounts of error.
So for the power subsystem, preparations for the next semester has almost been completed. The design for the 6-volt converter is done and just needs a few tweaks to send off to the manufacturer to fabricate. The budget has been updated with the bill of materials, and all that really needs to be done is to send it off for verification. The major challenges this semester include finding the models and footprints for the parts and checking if they fit the dimensions on the data sheets. Also, really just a huge learning curve for me was how I was new to the PCB designing process. So finding parts that fit specifications, simulating the circuits, and really just designing them from the ground up was new to me. So to go through the design, here's the schematic, the 2D and 3D model of the PCB. There are no design rule verification errors, and all that is needed to be added are the input and output voltage ports. The Gerber files I'm going to generate and send to the PCB manufacturer hopefully by the end of this month or 2 weeks, I don't know. I mainly used Webench to create and simulate the designs. Here are the results of the input transient simulation, which based on the results are acceptable with the output voltages maintained just under 6 volts from an input voltage around 10 to 12 volts. Next slide. For the steady state simulation, the output voltage seemed to fluctuate from about 5.94 to 5.96 volts, which is very acceptable. When the design is fabricated and all the parts soldered on, I'll be conducting more physical tests such as the line load regulation and the PSRR.
So fall 2020 plans, I briefly touched on part of my subsystem. But overall, we need to make changes to the physical structure of our system. We need to validate the code. We need to do laser research that we weren't able to do this semester. We need to get more accurate data sets to target the stem location, order, build, and validate the PCB, and then modify the design to a dynamic system.
Anybody have any questions? Thank you for listening.